Hello everyone. This video is for the proposed NSF Center for E-Design project, Parallel Computing and Network Modeling of Internet of Manufacturing Things. So this is a collaborative project with Dr. Kumara, and my name is Hui Yang. We are from Department of Industrial and Manufacturing Engineering at Penn State. So as we can see from this slide, Internet has been evolving in the past few decades. So from the pre-internet phase, that is human-to-human communication, to we have Internet of Contents, that is World Wide Web, and then we have Internet of Service, like Web 2.0, e-commerce, e-productivity. So now we have the, as shown here, smart IT platforms and service. And then it is evolved into the Internet of People, social media. For example, what do we have? The Skype, Facebook, YouTube. So we have smartphones and applications. And the next generation is an Internet of Things, machine-to-machine communication, including smart devices, smart objects, smart data. So we will have identification, tracking, monitoring, metering, and automation, actuation, and payment, those kind of Internet of Things. So we are moving from the Internet of People to Internet of Things. So 2010, world population is 6.8 billion, but connect device is about 12.5 billion. By 2020, world population is going to increase to 7.6 billion, but the connect device is going to be 212 billion. So we have people connect to the Internet, and now things connect to the Internet, and in the future, things are going to be connect to things. But so those Internet of Things generate big data. But what is the next step? We need to extract useful information from the data and then derive the useful knowledge about the system we are studying, for example, the manufacturing system, and then develop a better understanding of the system dynamics and then better control. So this is data to insight to action. So we have data and then descriptive analytics and then prescriptive analytics. So what is smart manufacturing? Smart manufacturing enables all information about the manufacturing process to be available when it is needed, where it is needed, and in the form that it is needed across entire manufacturing supply chains, complete product life cycles, multiple industries, and small, medium, and large enterprises. So physical world is going to reflected in the cyber world through the unprecedented access to data. But once we have the virtual machine network, how can we fit back the control actions or insights to the physical world so that we can have better scheduling and control and optimization of the physical systems? So this is called data-driven intelligence in the cyberspace. So not only the data enable us to build the virtual network, but we want to use the network to derive data-driven intelligence and then feed it back to the physical world. So let's have a look at this scenario, machine connect to machines. So we have a machine center. It can be connected to a power meter. And this power meter can check the energy consumption every millisecond. So for example, the acceleration of the spindle, and two-way drives, x-axis, z-axis, and cutting, and then the deceleration and the two-way drive again. So this is the energy profile in one cycle when we are cutting a part. But what if we have the wireless communication and IoT modules? We pass those data to the Internet of Things. What if we have many machining centers? Or we have thousands of them in the Internet. How do we build such a network model? So what we are proposing in this project is to do the network analytics for efficient representation and quantification of energy variations among networked machines in the large-scale IoT context. So each machine has its signature, and then we have the database of all the signatures. We want to do the pattern matching and then derive the similarity matrix. And then based on each machine's signature, we want to derive a network model. So for each node, it has attribute. Attribute will be the signals. And then we compare each machine to the other machine, whether there is any signature difference. Then based on the self-organizing network model, we will be able to see how the machines are organized and scheduled in the virtual network space. So we also call it cyberspace. So then we can have maintenance decision feedback to the physical world. So this is the basic idea in this project. So the challenges is first, right now the system generates big data, and we only do the deterministic network modeling and embedding right now, and also we are doing the serial computing with a single computer. But because of this give us significant challenges, we want to contribute to fast and parallel network modeling with stochastic network and parallel computing. So this methodology can be potentially used in manufacturing, supply chain, healthcare, and smart cities. So in this project, we are going to explore the fundamental methodology and then derive different applications. Okay, this is my contact information. Thank you very much for watching this video.